Good morning, everybody. This is Mr. Ainsworth, and I'm going to be talking about how to integrate polynomials this morning. And I mean morning, man, because it is about 6 a.m. Before school. So before I start, I'd like to talk about the two branches of calculus that we have been through and that we're going through. We have been talking about differentiation. That's our first branch of calculus. That's what you've been through in the last few months. And it's where you learned how to differentiation. Come on, Ainsworth. It's where you learn how to differentiate different functions. Okay, there you go. Okay, and we had certain symbols for that. We talk about dy dx. We talk about f prime of x. We talk about y prime. Okay, and then there's what's called the antiderivative. Okay, which is the inverse operation of the derivative, also known as the integral. So you're going to learn how to integrate or anti-differentiate in this next few lessons here. We're going to be going through. It has a special symbol that we use, and there are two branches actually of the integral, or two main types of integrals basically. One called the indefinite integral, which we're going to be starting with today, the indefinite, and then the definite type, okay, where you evaluate the integral from an upper and lower bound. Indefinite integral. So the indefinite integral looks like the integral of f of x dx. It's the elongated s here, stretched out s. And then if you evaluate it from an upper lower bound, column A and B, you have what's called a definite integral. Alright, so our first main goal in this lesson is just to be able to integrate functions of the type of x to the n. Alright, some polynomial form where n is some, well, it could be rational as well. So it's not just a polynomial form, but x to some power n where n is a rational number. Okay, so we're going to learn how to integrate, or take the antiderivative of x to the n dx. So we have a theorem for that to help us out. Our first main theorem states that cap f of x, capital f of x, is an antiderivative, or is the integral, okay, of a function f, known as lowercase, if you differentiate cap f and you get the lower function. Okay, not the lowercase, or the lowercase function f of x. For all x, okay, the upside down capital A means for all x on the interval. Okay, this means for all. Okay, in other words, if you integrate or take the antiderivative of f of x, you get a function called cap f of x plus some arbitrary constant here. And the reason why is because if you differentiate cap f, you get the original function. So we're going to be looking for functions whose derivative is f of x. Alright, now the history of the integral, well, it actually represents an infinite sum. It actually dates back to Leibniz and Newton, which you're going to research pretty soon. And because it represents an infinite sum, we use the symbol that looks like that. It looks like the elongated s right here. The symbol elongated s for the integral, because it actually represents an infinite sum, as you're going to find out later on. Okay, now the c right here that I was talking about earlier, it's called a constant of integration. Okay, and it's necessary, so let's talk about that just for a second before we start integrating different functions here. There's a reason why we need that constant, but why? So let's take a look at a few functions here. First one f1, and let's call it x squared plus 3. Second function f2, let's say x squared minus 9, and f3, let's let it equal to x squared minus 50. Alright, if you differentiate all these functions here, we're going to get the same result, because no matter what constant is involved in the functions, the derivative of the constant is 0. So if I differentiate f here, all of them, where I is 1, 2, 3, and so on, f prime is going to be 2x. All right, for f1, where let me just say where I equals 1, 2, 3. Okay, meaning that if you differentiate all those functions right there, you're going to get 2x, no matter what the constant is. So if you integrate 2x, we could get any one of those functions right there. We can get f1, we can get f2, we can get f3. Because remember, the integral is just the inverse operation. So if I can get from f to f prime, I should be able to get f prime back to f. And that's through integration or finding the antiderivative. So that constant's necessary because it doesn't matter what the constant is. Oops, right here. It doesn't matter what the constant's 3, -9, -50, 1,000, 1,000,000. If you differentiate, you get 0. So if you integrate, we need to get back to that constant. Okay. So let's go ahead and take a look at how we integrate functions of that form. So in this first one here, what we want to do is think of a function whose derivative is 3x squared. Remember, this integral is a function whose derivative is 3x squared. Okay, now it has to be a degree higher because whenever you differentiate a polynomial function, it decreases by a power of 1. Just remember, the derivative of x to the n is equal to n times x to the n minus 1. So it reduces the power. It reduces the power by 1. So if the differentiation reduces power by 1, then integration must increase the power by 1. So this must be a cubic function, and it has to be x cubed because the derivative of x cubed is 3x squared. But you have to put this constant of constant of integration in there, because if you differentiate the constant in the function, you get 0, and the derivative of x cubed becomes 3x squared. Okay, so I'm going to make a little note here. Why? Well, if you differentiate d dx, okay, of x cubed plus 3, you get 3x squared. And notice that's the original function here. So you can check all your integrals by differentiating your result, and it should be equal to the original function f. So this right here is little f of x, and this is cap f of x in my theorem above. Okay, this f of x, capital F of x, is a function whose derivative is lowercase f. Okay, so that's how you got to think. You got to switch your thinking a little bit. Okay, on this next one here, we're looking for a function whose derivative is 4x cubed. So I'm going to start by saying, hey, it's got to look similar to maybe 1 degree higher, like x to the 4th. And you got to be thinking, what's the derivative of x to the 4th? Well, it's 4x cubed. All right, but you got to add a constant of integration right there. Let me make a little note again. Why? Well, if you differentiate your result, x to the 4th plus c, all right, you get 4x cubed. And again, that is the original function here. So differentiate result, get the original function, and that's your correct integral. Okay, it's not always that easy though. So you want to be looking for some patterns. For x to the 9th, you want to be thinking of a function whose derivative is x to the 9th. So let's try x to the 10th. Now if you differentiate x to the 10th, you get 10x to the 9th. And notice there's no 10 there. Okay, so no problem. Go ahead and divide it by 10. And just adjust it. So if you differentiate this right here, you get 10x to the 9th for the numerator. Divide that by 10, you get x to the 9th. And of course you got to add a c there. So again, once again, you just add a power and then adjust it by a division if you need to. But if you notice here, there's a specific pattern. If you add 1 to the exponent, you're always going to add 1 to the exponent because the integration is always going to increase the power by 1. And to adjust it, you're going to have to divide by that power, the same power right here. So I can say in general, and this is our power rule for integration right here, that the integral of x to the n dx is going to actually equal x to the n plus 1 divided by whatever n plus 1 is, and then of course plus c. Now we have a couple other theorems that we're going to need. All right, the first one deals with like how to deal with a constant here. K is some constant. And if you integrate the integral k times x to the n dx, what you're going to be able to do is distribute out the constant here and rewrite it as k times the integral of x to the n dx. It's going to make it easier to evaluate. And since we already know how to differentiate a sum or difference, the derivative of a sum is the sum of the derivatives, and the derivative of difference is the difference of the derivatives. Same thing applies with integrals. The integral of a sum or difference here, sum or difference, is actually the sum or difference of the two integrals independently. So I'm going to integrate f of x dx and then add or subtract the integral of g of x, which is just another function in respect to x. We say dx. Okay, so let's learn how to kind of work with those three theorems there. First of all, our first constant here is 5, so it's very synonymous in the second case there, where k is 5 here. I can distribute that out and write it as 5 times the integral of x to the 7th dx. So really, you don't even have to focus on the 5, the constants. You don't have to worry about them. You just have to worry about the variable term, the x to the 7th. I know it increases power by 1, so I get 5 times x to the 8th. Right? I have to adjust it, and I have to divide that by 7. Okay. The derivative of x to the 8th is 8x to the 7th, and there's no 8 there. So I have to divide it by 7 to adjust. Or simply use your power rule here for integration. And then, of course, you add your constant of integration. You can check this derivative, or excuse me, this result by differentiating. So just remember, check by differentiating. Alright, next one, it's a sum and difference of terms. So what you do is you just integrate each one independently. So what you have here is the integral of 5x dx minus the integral of x squared dx plus the integral of 2 dx. So you integrate independently. And so you're looking here for, well, first of all, you can distribute out the 5 if you like and write it as 5 times the integral of x dx. And then minus whatever this is. Now the integral of x squared, well, let's see, it's got to be a cubic function, right? Okay, but the derivative of x cubed is 3x squared, and there's no 3 there, so you got to divide that by 3. Or you can think kind of like using the theorem. You can add 1 to the exponent. So 2 plus 1 divided by 2 plus 1, which is 3. You get the same result. And then what's the derivative of 2? What's the derivative of what function gives you 2? Well, it's 2x. So you have to add 2x here, and then plus some constant of integration. And if you're thinking, hey, where did all the 3 constants go? Well, you're right. There's a constant for the first integral, call it C1. There's a constant for another one, C2. And for the third one is C3. And if you add all those 3 constants together, you get just another constant. So what we say in general is that if there's multiple constants in the of integration, just represent it one time, because a constant plus a constant plus a constant is just yet another constant. So only write the constant once. And then on this next one here, we got 5 times x squared divided by 2. You have to add 1 to the exponent divided by that number. And minus x cubed divided by 3 plus 2x plus c. Now when it comes to functions like this, what you want to do is write in exponential form. Okay, I'm talking about x to the n, okay? So what we're going to do is we're going to rewrite the integral as 1 divided by x to the 1/3 power first, and then bring that variable upstairs and write it as x to the negative 1/3 dx, and then kick in your power rule. Okay, so you have x to the negative 1/3 plus 1 divided by negative 1/3 plus 1 plus some constant of integration. And then of course, you just go ahead and simplify a little bit. You get x to the 2/3 divided by 2/3 plus c. And then since anything divided by 2/3 is the same as multiplying by the reciprocal, we're going to get 3 halves x to the 2/3 plus c. Again, multiply by the reciprocal right there. Multiply by the reciprocal instead, which is this term here, the 3 halves. So dividing by 2/3 is the same thing as multiplying by 3 halves. That's what I'm saying. So remember that this is going to come up a lot, okay? Trust me on that. Okay, and the last one here, what I want to do is handle this one here, and what I'm going to do is something very simple. We want it again in exponential form. Okay, this technique happens all the time too, by the way. And all I do is split the fraction and rewrite it. So I get the integral of x cubed divided by x squared dx plus the integral of x to the fifth divided by x squared dx. Simplify both, I get the integral of x dx plus the integral of x cubed dx. Now use your power rule. Remember the integral of x to the n dx is equal to x to the n plus 1 divided by n plus 1 plus some constant. Okay, remember this is going to come up a lot. This is a theorem. Alright, that's how you integrate integrals of that form or functions of that form right there. I'm talking about functions of the form of x to the power of n. And I get x squared divided by 2 plus x to the fourth divided by 4 plus some constant of integration right here. Remember, the two constants combine to a single constant. And that's how it's done, my friends. So give your homework a shot and come to class prepared, and I'll talk to you tomorrow.